one thing I wanted to mention about the worksheet, but maybe I'll wait until hopefully we have more people showing up. The worksheet is distributed so you can start that, and I want to spend a moment talking about this first problem on the worksheet where the suggestion is to use an absolute value function for the u. So we'll get to that. We'll talk about that when, hopefully, some more folks get here. Now, where is my... Okay, so let's go to where we were. And let me remind you that we had started integration by parts. And integration by parts has this formula up here. We use the expression ultraviolet voodoo to remember it. The integral of u dv is uv minus integral of v du. And at its core, it's essentially a reverse product rule. It's how we integrate a product. Generally, that's how we think of integration by parts. It's going to have a lot of other applications, but that is sort of how it was originally developed, to help us integrate a product. So it parallels the derivative of a product. We know how to do that. Integration by parts is going the other direction. How do we integrate a product? So we did one example. Let's do a second example here. And when we look, we see that we do have a product here. And remember that in calc, when we say product, it could be a division or it could be a multiplication. Right? Division still is a product. And the key here is to identify u and dv. So we're always going to split the integrand into u and dv. And once we have it split into u and dv, then we have to find du and v. So on the left side, we're going to differentiate whatever we choose for u. And on the right side, we're going to integrate whatever we choose for dv to get the other two missing pieces. So in general, when you're looking here, the rule of thumb I gave you was that pick the biggest part that you can integrate easily and put it with dv. That generally is a great rule of thumb. There's some other acronyms people use to try to figure out what to let u and dv equal, but that's sort of a general principle that usually works. Let dv be the biggest chunk of the integrand that you can easily integrate. Now, let me ask you this. So here there's essentially two choices. When we're looking at this, we see the x squared multiplied by the natural log of x. So we essentially see two functions being multiplied together. You could be clever and say, well, isn't it also possible to think of it as x multiplied by x ln x? And yeah, you could do that. You could do some funky stuff. But essentially, when we look at that, we see two functions, x squared and natural log of x. And so the idea is that one of them's got to go in the u position, one has to go in the dv position, which goes where? And let me just ask you this. Can we put the natural log of x there? Would that make sense? If we put the natural log of x there, can you tell me what v would equal? I hear a no.
You probably can, but then you'd have to raise both to the e, and then you'd have to do a bunch of...
So what does e to the dv mean?
Yeah,
That's not something we've seen, right? Our differentials are already sort of attached to an integral symbol. Does anyone know how to integrate natural log of x? Maxwell, you do?
Isn't it 1 over x?
What's that?
Am I confused? Isn't it 1 over x?
Is that the integral of natural log x?
that's the derivative.
That's the derivative,
Okay.
right? It's super easy to make that mistake because every time we see ln x, we sort of think, oh, derivative is 1 over x. But here we're integrating. And this is what makes integration hard, is that we see common functions that we don't know how to integrate. You do not know how to integrate natural log of x yet. But guess what you're going to learn today? How to integrate natural log of x. We're going to do that today. You've been waiting for that, even though you didn't know it maybe. So we don't know the antiderivative for natural log of x. So this case actually makes it pretty, as long as as long as you recognize that you don't know how to integrate that, you really don't have a lot of choice here. You're going to stick your natural log of x there, and you're going to put your x squared there. So there we go. Now, what do we do on the left side here to get our du?
1 over x.
Yeah, 1 over x. And let's not forget the dx, because we are taking the derivative du dx is 1 over x, and then we sort of multiply both sides by dx to write it as that differential statement. How about v?
X cubed over 3.
X cubed over 3. Yeah, so simple power rule. Add 1, divide by the new exponent. So this is our little setup for integration by parts. We have now separated we've sort of taken this integrand right here, including the dx, and that's what we are creating in the top row here. We're taking our integrand and subdivided it into a u and a dv. So now we use our ultraviolet voodoo formula. This is going to equal u times v, and u times v is right down this main diagonal there, u times v. So that will be, normally we put the power of x in front of a natural log, so this will be 1/3 x cubed natural log of x. So that's uv, minus the integral of v du. Maybe I'll put this up here just so that you are remembering it. So u dv's integral is uv minus integral of v du. So that's what we're doing. So now we subtract off the integral of v du, and v du is the bottom row. So we are going to be multiplying these two functions together. So does that look like x squared over 2 to you?
X squared over 3.
X squared over 3. Thank you. X squared over 3. That's what it looks like. So we have that. And now we're almost there, because this is our point where we ask ourselves, is this integral easier than the original integral? And if it is, we've made a good decision. If that integral is harder than the original, then we probably made a bad decision here, and we would go back and try something different. Now, luckily, in this case, we didn't have a lot else that we could do. It seems to be working, so that's great. So then we just have to finish this off. So to integrate x squared over 3, same rule of thumb. Add 1, divide by the new exponent, so we're going to get x cubed divided by 3, and 3 times 3 is 9. We could write that as 1/9. And then a constant of integration, and there we have it. So that is our indefinite integral of x squared natural log of x. Any step there you want to ask about? Yeah?
Are we going to have to include the plus c always?
You tell me.
Yes and no?
Only if it's
No, not yes and no, it's one or the other. So this symbol here, indefinite integral, the result of that is always a family of antiderivatives. So if we don't have the c, then you have one particular antiderivative. But this symbol represents the collection of all antiderivatives. So we always need the plus c if it's an indefinite integral. And I think what you're thinking of might be this sub-piece here,
Right, yeah.
because we talked about this on Thursday.
Mhm.
In here, when you integrate x squared and get x cubed over 3, we're choosing the constant to be 0. And you could choose any constant you want right here. So it may look like we're not putting a plus c here, and it's because we need one antiderivative, not the whole family of antiderivatives. So here we choose a plus 0. But in general, we would have to use the plus c
When we are doing indefinite.
when we're doing an indefinite integral. Yeah. Correct. All right, let's go to this page. So I mentioned that the integration by parts process is usually thought of as a reverse product rule. It's usually thought of as a great technique to integrate products. But when we look at these two examples, there's no products there. These are two common functions that we don't know how to find an antiderivative for, though. We don't know an antiderivative for either of those. So integration by parts, it turns out, also works really well for some of these more obscure functions. So let's try this one. So once again, we want to separate the integrand into a u and a dv. And when we look at this integrand, there's only one function there. Where do you think it should go? The u or the dv? U. It's going to have to go with the u because we know how to differentiate it. And it can't go with the dv because we don't know how to integrate it. Yeah, we'd be back to the original problem again. So we're going to stick the inverse sign over here. Right there, we're going to put it with our u. And then dv, what's the only thing left?
dx.
The dx, exactly. That's all that's left. And so on the left, we differentiate. On the right, we integrate. So on the left, when we differentiate, we have du equals 1 over the square root of 1 minus x squared. And then we need a dx, which we can put in the numerator. That's fine. Integrating over here, and once again, we're choosing the constant of integration to be 0. So we don't need to put a plus c. We don't need to. You can pick any constant you want. If you want to be a contrarian, you don't have to pick 0. So now we do uv, and uv again is this main diagonal there. So that's going to be x ln of x, x inverse sine of x. So there's uv minus the integral of v du. V du is the bottom row. So v du is down here. Our voodoo is the bottom row. So that's going to be x multiplied by this expression here. So that's going to give us x divided by the square root of 1 minus x squared all times dx. How's it feel? Anyone? Gael, make sense? All right. Technique of integration for this integrand now? Caleb?
Could you do it again for the x over root of 1 minus x?
Good question. That's a great question. So right now we have a quotient, which is a product. So we could go with integration by parts again. Is there an easier technique that might be quicker, Sebastian?
You can take out the square of 1 minus x squared. Or it will be, sorry. You can take out the you can put it. You can write 1 over the square of 1 minus x squared, and then you have the x by itself in the inside of the integrand.
So let me just make are you saying take the square root of 1 and the square root of x squared?
No, just like to take it out of the integrand, and then you have the x by itself.
Well, we can't pull it out of the integrand would mean factoring to the front.
Okay.
But what kind of, we don't factor x's out to the front, only constants out to the front. U substitution? U substitution is going to be the way. And why do we know that U substitution is going to work here? When we look inside the square root or inside the angle or inside the denominator, those are our typical places to look for a U. And the key is that the derivative of U, or at least a multiple of the derivative, needs to be somewhere else in the integrand. When we take this derivative of a quadratic, we get a linear. We see a linear up top, so that's what clues us in that integration by that U substitution is going to work. Integration by parts could very well work again if we wanted to do it a more complicated way, but ideally we're going to go with something more simple. So, all right, so we're going to let u equal, so this is a regular u sub here, not an integration by parts substitution. So we do this kind of thing. And we are going to divide both sides of this by -2 because we want to isolate. And we're trying to get this to match. So there's an x dx, there's an x dx. Those match. So that's going to allow us to replace that whole numerator with du over -2. So let's keep trucking here. So we have our x inverse sine of x out there minus. So then we're going to have our integral here. The x dx part is going to become du over -2. So I'm going to put a du. And over -2, we can factor that constant to the front. So du divided by -2, I'm just going to pull that -2 out to the front. Constants can factor through derivatives and integrals. The denominator is a square root of just u. Square root of u. All right, we're on the right track. All of the letters inside that integral are now u's. That's good. Now, we need to do a little bit of rewriting in order to pull this off. How do we want to rewrite that square root of u that's in the denominator? U to the -1/2. Everyone okay with that? So u to the -1/2. As soon as we have that, as soon as we take that radical notation and we write it with a fractional exponent and then we move it upstairs, then we kind of see that we can use the power rule for integration. So let's go ahead and do that. Oh, dropped an x here. Inverse sine of x plus 1/2. So we're going to add 1 to the exponent here. I'll leave a little gap. So we add 1 to the exponent, we get a positive 1/2. Then we have to divide by that positive 1/2. Dividing by positive 1/2 is the same as multiplying by 2. And then we have a plus c. The 2's will cancel out. 1's in the numerator, 1's in the denominator, so those will cancel out. And the last thing we have to do is do some back substitution. There's our u right there. We just have to put that back in. And then we'll have our final result. So the square root of 1 minus x squared plus c. All right, is there any part of that? Stockton?
Why not just do, like, why can't we just have the, when we have square root of 1 minus x squared in the denominator, why can't we just pull it up and have it 1 minus x squared to the -1 power?
You can do that. Algebraically, you can do that. And then you're going to have another product. And if you do your u substitution there, you would end up with this same thing here. You'll still, if you pull that square root up to top, you'll have a product, and then you have that same question, how do we integrate that? And u substitution would be the way. So you can definitely do that. You can pull it up sooner rather than later. Totally fine. All right, you ready to try one?
Sure.
All right, let's go. So this antiderivative that you've all been waiting to know. How do you integrate natural log of x? Super common function. Let me know if you are struggling. It's going to look really parallel to what we did with the inverse sine. So again, we sort of see this pattern that there's only one function, there's not really a product. You're on the right track. And in this class, we'll be asked to find the antiderivative of natural log quite a few times. It's going to show up as parts of other problems. And so you will probably end up memorizing it. But it's not necessary, but you probably will just because you'll see it so much. Yeah, looks good. Yeah, what's going to go in there? So VDU, so that times that. There's not a lot left in there, is there? Let's see. So this should have a dx though, right? So it's uv, so u times v minus the integral of v du. So this right here, when you multiply these together, you get 1. So this should have a dx under there.
Oh, at the X.
When you differentiate this side, you
Right.
should have a du and a dx.
Oh,
Yeah, so there we go. There we go.
okay.
All right, so you'll kind of got it pretty quickly. So we're going to let u be natural log of x. We're not going to put the natural log of x over with the dv because we don't know how to integrate it. That's the whole point. So we're going to put it there. We know how to differentiate it. Remember, when you differentiate here, you need your dx on the right-hand side. You know, the idea here is if you have u equals ln x, the derivative is du dx. That's 1 over x. But then you multiply both sides by dx to get it over to the right so that we have a way to substitute. And integrating here, we'll get v equals x. And then u times v, main diagonal. So we'll have x ln x minus the integral of v du. V du is the bottom row. So that's going to be x times 1 over x, which is just 1, multiplied by dx. So we have that. And the integral of a differential is just x. And then we have our constant of integration. So that is our elusive antiderivative. And how would you double check? If you look at that and say, whoa, that's the antiderivative of natural log of x? What would you do to that to check that you didn't screw up a sign or something?
Take the derivative.
Take the derivative, yeah. And if we take this derivative, what rule are we going to use for that first piece? Product rule, because that's a product. X ln x is a product. So we would do that. Yeah, good. Good, good, good. Let's talk about the worksheet for a second. We have more folks here. I just want to mention a couple of things about the worksheet. So the worksheet for Chapter 8, it looks very similar to what we just did. We were integrating the natural log function. But notice that we're integrating the natural log of an absolute value. And the suggestion that I want you to do for this substitution is to let u equal that. I just want to talk a minute about the derivative of a piecewise defined function. Because normally, when we take a piecewise defined function, so let's just take the absolute value of x for a moment, and the definition of this piecewise defined function is this, that if what's inside the absolute value is positive, its value is found by just erasing the absolute values. And if what's inside the absolute value is negative, the way you make it positive is to multiply by -1. So that's what the negative x does. It takes the x value and changes its sign by multiplying by -1. But when you differentiate this, so let's just suppose we call that f, the derivative of a piecewise defined function, it depends on which piece you're on. The derivative of a piecewise defined function usually is a piecewise defined function. And when we look at the graph of the absolute value function, the derivative represents the slope. So tell me this. First off, the derivative of this upper piece, derivative of x is 1. It's the coefficient. It's the slope. What is the interval on which that is true?
0 and infinity.
So it's greater than, so it's 0 to infinity, right? So this is x greater than 0. This is x less than 0. Do you see the difference? Absolute value function is not differentiable at that vertex, right? So that point where x is 0 is getting left off. So this function's derivative is not defined on the entire real line because we have a point of non-differentiability right here. The derivative on the left is going to be -1. Derivative on the right is going to be 1. So in general, this looks like a pain to use an absolute value function because when you take its derivative, you get a piecewise defined function normally. I want you to pay careful attention to that. Go through this same process and see if the derivative of this piecewise defined function is also a piecewise defined function. It may not be in this case. So think about that as you're playing with it. Because ideally, whatever you let u be, in order to create uv minus integral of v du, ideally u is not a piecewise defined function. That'd be kind of weird. Piecewise defined function times v. So play with that. Carefully go through this same process. Caleb, question? All right, so that's just a heads up on the worksheet. The other thing I wanted to just mention quickly, the videos that are not required, but we're starting a new set, and Gabriel's Horn is the first one. Super tasks for next week. Super tasks is a good one by, I'm sure most of you math people know, Vsauce. You know Vsauce? If you don't, then definitely watch it if you don't know who Vsauce is. Does anyone not know who Vsauce is in here? Has anyone not seen one of his videos?
I mean, I might have, and I don't remember it.
Yeah, he's a super fast-talking, math nerdy guy that makes really cool animated videos about, like infinity and things that are interesting. And this one is a really good one. This a combination of Vsauce and what's the guy from MythBusters? Adam Savage. So that's a really good one too, with the two of them working together. But we'll talk about that one later. So start watching a couple of those. Pi is Wrong is a classic one. Do you know Vi Hart? Vi Hart, she's the one that does this one. She makes super cool videos about she does all sorts of cool art math combinations, and I don't know if she still works for Khan Academy, but she became their math magician or something for Khan Academy and did a bunch of stuff for Khan Academy also. So that's a good one. So we're kind of in this section right now though. Again, just fun videos to watch for nerd purposes. All right, let's go to this. Let's see, so okay, let's keep that up there so we see it. All right, so let's do a couple more examples. I'll do the first one, you can do the second one. This first one here, notice the notation, little weird. I had never seen this until this textbook, where the square of the log function is sort of done in the same way. Makes sense. Same way as we do the square of a trig function. We put the two on top of the function itself. Normally, all the books until this book that I've ever seen, natural log of x squared, you'd have parentheses and the square on the outside. So, just be aware that that means natural log of x quantity squared. So I'll go through this one. Now, once again, when I stare at this, I see two functions. And yes, you could be clever and mix an x with an ln squared or an x ln x times x ln x, or you could do all sorts of weird things. But let's just pick the most natural subdivision into two functions here. I see those two functions, and I'm saying to myself, okay, one of them has to go with the u, one of them has to go with dv. Well, natural log squared of x we actually know how to integrate natural log, but now, because we just did it, but we probably don't know how to integrate natural log squared. So the natural thing out of the gate would be, hey, let's put the natural log squared there. Let's put the x squared over here. And let's build our little formula table here. So that would be a natural first choice, picking the u and picking the dv. Now here's the classic place to make a mistake. Remember, natural log squared, the square is the outer function, even though it may not look like it the way it's written here. So that square is on the outside, so we bring the square down, subtract 1 from the square, giving a power of 1. So 2 natural log to the 1, and then what do we have to do?
Integrate the x squared.
Say that again?
Take the antiderivative of the x squared.
Not the antiderivative,
The derivative of ln of x.
the derivative of ln of x. So remember that this is how it's looking. And when we take its derivative, that 2 comes down, that makes the base have a power of 1 now. So it's 2 ln x to the 1 multiplied by the derivative of ln. Right? Because ln is the base of this exponential expression. So then we have to multiply by 1 over x. So that's going to be a division by x, and then we need a dx in here. And then over here we have a pretty standard thing. All right, any questions on getting that stuff? Getting our parts. So then u times v, that's the main diagonal here. So uv, we multiply these together. So that'll be 1/3 x to the 3 natural log squared of x. If you don't like the look of that, Garrett, question? If you don't like the look of that thing, you put natural log of x quantity squared. If that just freaks you out, write it as natural log of x quantity squared like all the other books. I don't know if this is a new trend. I haven't looked at many books lately. So uv minus the integral of v to u. V to u is the bottom row here. So v to u, we're going to take that and multiply it by that. So let's see if we can do it. We're going to have 2/3. There's a 2 over 3. This x is in the denominator. There's 3 x's in the numerator, so we'll end up with an x squared. So let's see. So 2/3 x squared, and then natural log of x. Does that look okay to everybody? So we took that and multiplied it by that. This x is in the denominator. It makes an x squared in the numerator. The 2 and the 3 can combine, and we end up with that. And here's our crossroads. We say, is this integral easier than the original? Does it look less complicated? Yeah. It looks better, right? What's different? Well, we jacked the power of natural log down a notch. Right now it's the power of 1, so it's working. So integration by parts is going to slowly get us to a place where we can integrate that without a complicated formula like integration by parts. But what are we going to have to do again? Integration by parts a second time. Yeah, we'll have to do it one more time. So let's give ourselves a smidge more space. So another integration by parts. And when we do this integration by parts, we are going to have a whole separate set of u's and dv's. Now, that 2/3, you could factor it out, correct? It's a constant. Constants factor through integrals. We could factor it out. My recommendation is not to factor it out, because you know that we have this formula here. If we factored out this constant, we would have a constant sitting in front of all of this, and then you would have to distribute it back in the end. It's super easy to make mistakes when you do that. If you leave the constant in here, it's going to come out in the wash a little bit easier. There'll be less chances of making that distribution mistake. So I'm just going to leave it there. And as you do more and more of this integration by parts, there's another clever trick that can be helpful, and that's with this minus sign. Because we still are going to have a minus that sits in front of these big red brackets. Because it's going to be minus, this integral is going to turn into a uv minus integral of v du. And as you do more and more of these, it's actually really clever and helpful to make that a positive and put that on the inside. Then you don't have to deal with the distribution of the negative sign in the long run. So I'll do it that way. It doesn't matter as long as if you're a good note keeper, if you're a good accountant, the brackets aren't going to freak you out and it'll be fine. But I'll do that little thing there just because it's going to make my life a little bit easier down the road here. So looking at the inside, I am now seeing this natural breakdown of the functions. I see that function and I see this function. So that's what I'm going to go with. So once again, I'm going to put the natural log over with the dv. So u is going to be everything in front. So negative 2/3 x squared. dv will be ln of x. Oh, I said I was going to do it the same way, and I didn't do it. So u is going to be the natural log of x. I'm going to keep the natural log of x with u, and then the dv is going to be the polynomial part. So we have that. Okay. So we're going to do what we normally do. We're going to find the du by differentiating. We're going to find the v by integrating and choosing the constant of integration to be 0. Okay, so that is going to give us this function out in front, and I've changed this to a plus by pushing the minus on the inside, so it's plus. Now I don't have to deal with brackets. If we had a minus there, we'd have to put big brackets for the uv minus integral of v du. So uv, main diagonal. Okay, main diagonal is going to be negative. This times that, that's going to be negative, so I'm going to just erase this plus, and now it's a minus because of this. Minus 2/9 x cubed natural log of x. So there's the uv. uv minus the integral of v du. Is v du positive or is v du negative? Just v du. When we multiply these two, are we getting a positive or a negative? Right, that's a negative there, which is going to make this turn into a positive. Yes. So, and it looks like to me 2/9 x squared. And there's our crossroads again. We asked that question, at least, hopefully we ask ourselves that question. Is this integral easier than the last? Yes. Now there's no natural logs. We don't even need integration by parts anymore. So we can immediately finish it off. So our final answer is going to be this big old mess.
Question. When you were doing the integration by parts the second time around, does it matter where the constant goes?
So when we're doing this integration, so this constant right out in front, this 2/3 piece, it does not matter. So that's a great question. So if you wanted to, if you do that little negative trick like I did and made that negative so that this is positive, you could put the negative 2/3 with the x squared or the negative 2/3 with the natural log of x, and it would work out exactly the same.
Okay.
You could even be, the ultimate contrarian and put a 2 with the x squared and a negative 1/3 with the natural log of x. You could do whatever you want to do. It'll all come out the same. Yeah. All right. You all try this one. So integral of x squared e to the 4x. Integration by parts is a natural choice because you have a product that cannot be integrated with just a u substitution. So go ahead and see if you can do this one. There's lots of these that you could do either way with your u and your dv. There's many that there's multiple ways that will work. And I think we're going to see some interesting, we're going to come across some interesting things here.
I made it worse.
Exactly. And if you make it worse, go back. Yep, go back and a couple of you are going to also get to the point where like Hayden just encountered, and you're going to end up with a worse integral. So as some of you are now seeing, depending on what you pick for u, you could end up with a worse integral. And the rule of thumb here, let me make a general comment. Let's just think for a second. If you put the x squared with the dv, isn't the power of x going to grow? Right, power of x is going to grow. And if you put the e to the 4x over here, it's just going to stay in e to the 4x, essentially, a multiple of e to the 4x. So that's another sort of thing to have in your mind. Generally, we say pick the biggest thing that you can easily integrate, or the most complex thing. E to the 4x is more complex than x squared. Putting that over with the dv is going to take the most complex part and stick it with the dv. You can integrate that. And then what happens to the power of x with the u? It's going to go down, right? Because you differentiate it, so that power is then going to go down, which is going to be more advantageous. Because the e to the x, whether it's with the u or the dv, is going to stay essentially the same. Yeah. Going with that. What will be our antiderivative there? So for an exponential, you always get itself first, and then we're going to get that 4 units, so we get it exactly as it is first. And then what do we do with that exponent? So if you were differentiating, you would use the chain rule. And if you're finding an antiderivative, you use reverse chain rule. And so what is the derivative of that exponent? 4. You just go divide by the 4. So if you were differentiating, you would multiply by the 4. And then how about over here? Yep, perfect. Yep. Spot on. Yes, exactly, and that's what you want to do. Oh, well, you see, you did do it. That's right. And then when you do your, so then now that that's a plus, your UV is going to be negative. That looks good. Yep. Minus. So there's no more distribution yet. Because this is positive, there's no distribution. It's just UV minus integral of V to U. So UV happen to be negative, minus integral of V to U. Now when you look at your V to U is negative, so that's what's going to force that down. Yeah.
Okay.
But it's not a distribution at that point, once you have pulled that minus on the inside. Don't we love those little digital erasers? And just make sure to put a dx there, so that it, maybe you brought it back. Yeah, that was great. On the right track. Very well.
Good one.
Good. Good. Yeah, you are on the right track for sure. UV, how is that a 3 and not a 4? Oh, and then your 2 ended up in the denominator here. Yeah, so that should be a 4 right in the denominator. And then over here, it's the integral of V du. You're multiplying these two, so that becomes, oh, I see. Yep, perfect. Good.
And what was that?
Just a 1.
UV. Okay.
Yeah. Yeah. Just leave it like that. Yeah. Yeah. So we're cruising. Cruising. I'll try to catch up to y'all. So the rule of thumb is that in this case, letting u be the power of x, that's going to be the smart thing, because as we differentiate, that power of x is going to go down and make our integral simpler. So this is what we should have for our setup here. uv minus the integral of v du, that's the bottom row. 2 over 4 is a half. So we end up with 1/2 x e to the 4x dx. Is there any question on that step? Everyone remembering integral of an exponential? If the exponent is linear, we can do the whole reverse chain rule thing. The integral is itself divided by the derivative of the exponent. We now see that our integral is easier. So that means we're on the right track. And now I'm going to use that little trick again. I'm going to push this minus sign to the inside. That's just going to make it simpler in the long run. You don't have to, as long as you're careful with your distribution. So u, and once again, I'm seeing this as a natural break, right? These two functions. And we're going to use the same pattern that we used up here. The x thing, the x expression is going to go with u. So I'm going to put minus 1/2 x here. And then for dv, I'll pick, once again, the exponential. And derivative over here, minus 1/2 dx. Integral of an exponential is itself divided by the derivative of the exponent. As long as that exponent is linear, reverse chain rule works. Yell if there's a step here you're not sure about or not following. So because that's a plus, I can just go straight ahead and do uv minus integral of v du. I don't have to do any distribution. So uv is right here. That's going to be negative 1/8, negative 1/2 times positive 1/4, and then x e to the 4x. So there's uv minus the integral of v du. I look down at v du is negative. So if v du is negative, that negative makes that negative a positive, and we're going to have 1/8 e to the 4x dx. How's that look? Pretty good?
Is it
Okay.
required to, like, if the first round of integration, we used E on the
dv.
dv, do we have to use it again on the second one?
Really good question. So if you were to say, hey, let's try and put the e's over here in the second one and the x's over here, let's think about what's going to happen. If you put the x's over here and you integrate, is the power of x going to go up or down? It's going to go up, and you're going to end up back where you started.
Okay.
So if you're doing integration by parts twice and you switch for the second integration by parts, you're going to undo what you just did. And you're going to end up back at the beginning. Yeah, so if you, and that's going to be the rule of thumb anytime you're using multiple integration by parts, is stick with the same pattern. If the exponential's on this side, keep it over there. Yeah, good question. So now we're to a point where we can integrate immediately. We don't need integration by parts anymore. We can just use our reverse chain rule. The integral of an exponential is itself. And if the exponent is linear, take its derivative and divide by that derivative. So 4 times 8 is 32, so that will give us this as our final answer. Issues? Jesse, question? You have a puzzling look on your face.
Why is the second one negative?
This negative right here?
Yeah.
Okay, so this right, so with our second integration by parts, this part's already here. Let's see if I can outline. So this box right there is going to become all of this, correct?
Yeah.
So that piece right there is this u times v right here. That is the uv, which is negative, right? That times that is negative. That's why that term is negative. Other questions? Do you see it? All right, so there we go. We can also do integration by parts with definite integrals. We have a couple here to do. Let's do, I'll do one and then we'll take our break and then you can do the other one. I'll do the harder one. The one, which one of those looks harder?
Arctangent.
The lower one? Lower one looks pretty gnarly, so we'll force me to do that one. And you all can do this one. So let me go through this one, then we'll take our break, and then you can work on the other one. So again, with integration by parts, we want to identify two functions normally. And we've seen that sometimes that second function is really just the constant one. But when I look at that, there's a clear product there. Y times arctan of y squared. The choices, let's see, we have a choice for u and a choice for dv. Putting the arctan with the dv would mean that we need to integrate arctan to get to v. We don't know an antiderivative for arctan. You know a derivative, for sure, but you don't know an antiderivative. So that tells us right away that we really don't have a choice. We are going to put the arctan with the u, and then whatever's left is going to go with the dv. So here is our integration by parts recipe. Now we need to get du. The derivative of arctan. So remember, derivative of arctan is 1 divided by 1 plus x squared, derivative of arctan x. So we have to be a little careful. First off, we're using y's instead of x's. So it's going to be 1 over 1 plus, instead of x squared, it's going to be y to the 4th, right? It's whatever is inside the arctan gets squared. All right, so 1 over 1 plus x squared, well, if y squared is playing the role of x, then y squared gets squared and becomes that. And then what?
Multiply by the derivative of the inside function.
Multiply by the derivative of the inside function. So don't forget the chain rule here. So we're going to have a 2y in the numerator, and we need a dy in there. I'll just put it in the numerator because there's no space. So that's the derivative. If we blow the derivative, we're hosed, right? And then we're going down the toilet bowl. So we've got to be able to do our first derivative correctly. There's your Calc 1. And then over here, we just get a y squared divided by 2. So this will be u times v. So this main diagonal right here, that's first, main diagonal, so uv. That's going to be 1/2 y squared arctan of y squared. This is a definite integral, not an indefinite integral. So this uv part will be evaluated, so we'll put our evaluation symbol there. So there's uv minus the integral. That also is going to need the limits of integration here. So uv minus the integral of v du. v du is the bottom row. So let's see, what do we have in that bottom row? All right. I see that the 2's are going to cancel. Do we agree there? We've got a 2 in the numerator, a 2 in the denominator. Those are going to cancel. So I'm seeing a y cubed in the numerator divided by a 1 plus y to the 4th. Any disagreement? Everyone see the same thing? Okay. Now, that integral, definitely easier. There's no more inverse trig function, so we're on the right track. What form is that integral in? Almost. Log form? Almost in log form? Remember that we think about an integral being in log form when the denominator's derivative is the numerator. Right? That's what's happening here. That's the pattern that is not so obvious here, but that's log form, right? The derivative of the bottom is the top. So we want to, once we know that it's in log form, then we have a very easy way to get rid of it. Whoops, how do I get rid of that? So what do I need to make it in exactly log form? Right now it's ish.
You need to do u substitution for the denominator.
You could do, so u substitution is the general way to do this, but if we put it into log form, we can skip. Remember those 6 steps that we can skip?
Yeah,
Which
it's
we
just the
like?
natural log of the absolute denominator.
Yes, exactly. So how do we make that numerator match the derivative of the denominator? Multiply by 4. Right? If we put a 4 right there, now the denominator's derivative is in the numerator, but we can't just do that. We have to balance it out by putting a 1/4 out in front. So we multiply by 1. Multiplying by 1 is our magic bullet. When in doubt, multiply by 1. And then the antiderivative is exactly what Caleb just said. So now we could evaluate this right away, but when we get this antiderivative, it's also evaluated on the same exact interval. So I'm just going to do all the evaluation at once instead of doing it in 2 separate steps. So now we have this front piece, this front function is being evaluated 0 to 1 over root 2. This piece is in log form, so the antiderivative is natural log of the absolute denominator. And that's getting evaluated on the same interval, so we can just do the whole thing all at once. Whole thing all at once. Let's just look at the 0 for a minute. When we plug in this 0 here, what is this function going to have as its value? 0. Because that y, if you plug in a 0 right there, 0 times anything is 0. What is arctan of 0, just out of curiosity?
0.
That's also 0. Arctan, remember the graph of arctan. We're going to see this function ad nauseum this semester. So the arctan function looks like this. It's one of the first functions that you ever see that has 2 horizontal asymptotes, one at pi over 2 and one at negative pi over 2. So arctan of 0 is 0. So just keep that in mind. If we were graphing the arctangent function, that's what it would look like. So we've discovered that plugging in 0 here is 0. What do we get over here when we plug in 0?
Natural log of 1.
Which is
0.
0 also. Everyone agree? So 0 is not going to contribute anything. So we just have to focus on that upper limit. So 1 over root 2 squared is going to be 1/2. 1/2 times 1/2 is 1/4. And then we're going to have arctangent of, again, squaring that gives 1/2. Minus 1/4 natural log. In here, we're going to have 1/2 squared. 1 over root 2 times 1 over root 2 is 1/2. And then we have to do that again. So we'll end up with 1/4. We'll get 1 plus 1/4. Arctan of 1/2, is that a special angle? Every single time you look at an arc function, you should be thinking angle. Arctangent is an angle on the right of the unit circle. Arcsine is an angle on the right. Arccosine is an angle on the top. So when we see that, we should be saying, oh, what's the angle on the right half of the unit circle with a tangent of 1/2? Do we know the angle on the right half of the unit circle that has a tangent value of 1/2? We know a sine and a cosine in quadrant 1 that are 1/2, but not a tangent.
Isn't that just asking the slope? So when you be looking
Arctan is asking for slope, so do we know an angle in quadrant 1 that has a slope of 1/2?
Oh, no.
No. We know an angle in quadrant 1 that has a sine value of 1/2. We know an angle in quadrant 1 that has a cosine value of 1/2, but we don't know an angle in quadrant 1 that has a tangent of 1/2. So that's just some irrational number that we can't simplify. We're just going to leave it. So that just stays as is. Nothing we can do about that. And then over here, the only thing we would typically do is combine those and write that as 5/4. And that will be our final answer. Any part of that you want to ask about? All right, let's take our 10-minute break. You can stare at that for a minute. Ask me, I'll be here if you have a question on it. If you want to start on the next one during the break, you can. Your choice. If not, 10 minutes. We're at 35.
Well, because so slope derivative of natural log of 2x, because they keep just getting 1 over x.
Yeah, that's right.
Oh, okay, cool.
Yeah.
Thought it was in something wrong. Okay, thank you.
Nope, you are on track. You are
Yeah.
on track. So once again, there's no choice. We don't know how to integrate with mortal means the natural log function, so we put it with the u, and then we differentiate it. That, there's the problem with that. What is the derivative of natural log? 1 over x. Where's your u? Where am I looking? Oh, right there. Okay, yeah. And then dv. So dv, we have to break this integrand apart. So it's going to be u dv. So dv is only dx. Oh, you were writing sideways. Oh, I'm sorry. Yeah, I write vertically. Okay, I got you. Yeah, so your derivative, so this is du. Okay, yeah, that's 1 over x times dx. Times dx. And then your dv, you're picking to be just dx. And so then when you integrate that, you get v is equal to x. Yeah, yeah, that's right. Yeah. And then you go from there. So you have to use chain rule here. So it's 1 over 2x times 2. Times 2. Just the 2 because it's linear. And then, so those 2's will cancel. Kaylin, is yours on there?
E doesn't cancel out. Don't you get E?
Let's see, so 1 over, so this 2 is too many. 1, 2, too many.
1 times E.
Because when you take the derivative, you're going to get 1 over the inside.
Oh, wait, you
And
would
then
have
multiply by
negative.
the derivative of the inside. So it's 1 over
So you would get
2x
minus
times 2.
I'm trying to remember how low.
So if you have,
Well, I know ln E is
your inside is 2x. So derivative is 1 over the inside
Not even
multiplied by the derivative of the inside.
Yeah, so I don't think
Those
we
are
can.
cancel.
I don't think
So
we
you'll
can.
end up with just 1 over x.
So,
Which you'll see, so it's not going to matter. If you have natural log of 5x, its derivative will be 1 over x also. Alright, and then now do your UV. UV! How's it going? Yeah, that's good, that's good. That's good. Yep, yep, you're on the right track. And now, and so when we do this, when it's a definite interval, we just have to also put the evaluation there. You know, so you should put it
Oh,
there.
like this one.
Yeah.
And then I could move it up.
And then you can move it at the end, exactly, exactly. You get it? Looks good. We'll see if that's exactly right. It's mostly right for sure. Maybe it's all right. Okay, so we're going to let u be natural log of 2x, dv be dx. Once again, chain rule. If you mess up your chain rule here, you've got a long way to go, and you're going to be going down a rabbit hole. So remember that it's 1 over the inside for a natural log's derivative, multiplied by the derivative of the inside. So we're going to have the 2's cancel, and we'll be left with just a 1 over x as the derivative. So regardless of what the coefficient is, if we generalize this idea, if you have y equals natural log of kx, when you find this derivative, you're just going to get 1 over x. Because it's going to be 1 over the inside multiplied by the derivative of the inside, and those k's will cancel. So derivative of natural log 2x is just going to be 1 over x. And then the antiderivative over here is simple enough. And then we can move to the integration by parts formula, the ultraviolet voodoo, UV, ultraviolet. Ultraviolet's the main diagonal here, so that's going to be x natural log of 2x. And because this is a definite integral, we should be putting an evaluation symbol here. So that's the first part, uv, minus the integral of v du. V du is the bottom row, so we're multiplying 1 over x by x, and what do we get? We had just 1, so we're going to have 1 times dx. And this has limits from 1 to e. And you could evaluate this front function on the interval 1 to e right away if you want. I find it easier just to do all the evaluation at once. So we'll just wait. When we integrate this, the integral of dx is x from 1 to e. So then we'll substitute our upper limit of e. We'll get e natural log of 2e minus e. Antiderivative evaluated at upper minus antiderivative evaluated at lower. So minus this, we'll get a 1 here and natural log of 2 there, so it'll be minus natural log of 2. And then it will be minus a minus, so plus 1. So that will be our final answer. Any questions, comments? So let's see. We'll do volume of the solid here. So we've got this shape, 1 bump of sine x, 0 to pi. And we're going to rotate that. Our axis of rotation is going to be the y-axis. So we're going to go around the y-axis like that. And we'll see that we need integration by parts for this integral. So if we are going to rotate that around, does it make more sense to use a horizontal integration element, which would create a washer? And if we did a horizontal integration element here, that would rotate around and create a washer. There would be a hole because of this gap. Or does it make more sense to use a vertical integration element and get a cylinder? Which one makes more sense?
Vertical.
The vertical makes more sense. So there's our vertical at a random x. The horizontal doesn't make a lot of sense because we would have to solve, this is now horizontal, so we would have to solve the right side of this curve equals, we'd have to solve the left side of the curve equals, and then, subtract the two. That's not going to happen with this trig function. So we don't want to use horizontal. So we're going to use a vertical integration element. This is going to create a cylinder, and the radius of that cylinder is this distance right there. The height of the cylinder is the height of that red integration element. So let's refresh. We are finding the area of a cylinder or a shell. That's 2 pi times the radius times the height. 2 pi r is the circumference multiplied by the height. Gives us the area of the cylinder. Now, we chose a vertical integration element. How thick is that vertical integration element? Dx. So that means we're integrating with respect to x, which means the r and the h need to turn into x's. So when we look down here, we are going to replace, bless you, what is the r going to be replaced with?
X.
X. Make sense? Right? That's what x represents. If I can draw my representative integration element wherever I want, I say that it's going to be at a random x, and regardless of where it's drawn, this x means the distance from the y-axis. Well, the distance from the y-axis is the radius of the corresponding cylinder. So r is equal to x. The height, that is given by the function, right? The height right here between those 2 points is the function. That's what this function is measuring. It's measuring the distance from the x-axis, the height of the corresponding cylinder. So we're going to have a sine x right there. So there is our area function. We're asked to find volume, which we know is the integral of area. The 2 pi can come to the front, and then we are integrating the product x sine x. Limits of integration.
0 to pi.
So limits of integration are going to be wherever so it's going to be along this x interval where we imagine all the infinite possibilities for these vertical elements, and they range from 0 over to pi. So that will give us our limits of integration. And then we have a product in the integral. So if we have a product in the integral, if there's not a direct substitution that's going to work, there's no obvious substitution, no u substitution, and it's a product, then we think integration by parts is probably the best bet. So we are going to let u equal something, we're going to let dv equal something, build our little recipe down here. So let's think for a minute. There's 2 natural choices here. We've got the x, and we've got our second function sine x. If we put the x with the u and differentiate, the power goes down. If we put the x with the dv and integrate, the power goes up. Sine is periodic. It's going to derivative to cosine, integral to cosine. There's a minus in there somewhere. But it's going to stay about the same. It's going to be a sine or a cosine regardless of where it is. So what that tells me is that I want to stick the x over here because I know that's going to reduce the power, and the sine over here. So once again, that rule of thumb that, hey, pick the most complex part of the integrand and put it with dv, as long as you can integrate it. The most complex part that's easily integrable. Sine is more complex than x, so that rule of thumb will work just fine here. We'll get a du equals dx, we'll get a v equals negative cosine. And let's see if that, in fact, gives us something easier. So we have 2 pi. Oh, and here's one of those situations. Well, let's go through it. I didn't think kind of ahead. I've got a constant out in front. You'll see that I need to put the big brackets. So we talked about if you have a constant out in front, it's usually, there's less writing if you keep it on the inside. Let's not do that this time. Let's keep it on the outside since that's where I put it. But we'll need big brackets for that whole uv minus integral of v du thing. So we're going to have 2 pi times uv. uv, once again, is this main diagonal. So uv is going to be minus x cosine of x. All right, and that has to get evaluated on the integral, on the limits of, on the interval 0 to pi. So there's our uv minus the integral of v du. v du is the bottom row here, so that's minus cosine of x dx, so that's going to be plus cosine of x dx. Close the big brackets, put the integration limits here. So we'll have that. So if I were to have put left the 2 pi inside, then you just don't have to deal with the big brackets, and the 2 pi just, is on the inside already. Okay, so let's integrate, and then we'll do all the evaluation at once. So we have minus x cosine of x. Antiderivative for cosine? Sine. Derivative of sine is cosine. Anti of cosine is sine. So that. And we are going to go 0 to pi for the whole thing. One thing I noticed right away is that the sine function at 0 and at pi will have a value of what? 0. So this function is not going to contribute. Sine of pi is 0. Sine of 0 is 0. So that function is not going to contribute. So let's see what we end up with. So we have our 2 pi out in front. Plugging in, how about cosine of pi?
-1.
-1. Cosine of pi, we're over on the left side of the unit circle. Cosine is the x-coordinate, so that's -1. So we're going to have negative pi. So pi is going in right there for the x. Negative pi times -1, positive pi. And then we subtract off this antiderivative at 0. What's x cosine x at 0? 0. So we end up with this as our volume. 2 times pi squared. That'll be the volume. Any questions? Yep.
Is this a cylindrical shell problem right here?
Yes.
Okay.
Yep. Cylindrical shell. When the axis of rotation and your representative element rotates around, it's going to create a cylinder.
Right.
When the axis and the element are parallel, you get a cylinder. When the element is perpendicular, you get a washer if there's a gap. But if there's no gap, then you get a disc.
Okay.
So we have disc, washer, and shell. So our shells are always cylindrical shells. Now that you have integration by parts dialed, we're going to add a twist. Integration by parts with a twist. Don't ask your tutor about integration by parts with a twist. They won't know what that means. But that's what we're going to call it in here. Integration by parts with a twist. And it will be, all will be revealed. So, when we look here at this integrand, once again, we see two well-defined functions. We see a very natural choice. We have the exponential function, we have the sine function. Let's just think for a minute. If we put the exponential function with the u or with the dv, when we differentiate or integrate, it's still going to be an exponential function. Right? If you take an exponential function and keep differentiating, it doesn't change. The coefficients change, of course, but it's going to stay exponential function. Same thing if you put it with the dv and you start integrating, it's still an exponential function. The coefficient might change, but it's still exponential. The sine also has that circular nature. The derivative is cosine, so if you differentiate or integrate, you're getting to a cosine, and it will repeatedly bounce around between sine and cosine. So you have these two functions that are going to be sort of indefinitely spinning, and that is what sort of is the nature of integration by parts with a twist. So we're doing everything the same. It will not matter which one goes with the u, which one goes with the dv. If you are more comfortable differentiating trig functions than integrating trig functions, then put the trig function with the u. If it doesn't matter, then do whatever you feel like doing. So I'm just going to do it like that. So a derivative of u here, chain rule. Oh, I'm losing space. There's a dx down there. And there is a minus sign there that is hard to see. Okay. So chain rule. The derivative, minus sign looks too far away. So derivative of an exponential is itself, multiplied by the derivative of the exponent. Over here we're going to integrate integral of the sine function, negative cosine function of the same angle. But then we have to do reverse chain rule and divide by 3. So you can put the 3 underneath, you can make a 1/3, whatever you want to do. So, last Thursday I said sometimes it's convenient to call the integral something. When you're doing integration by parts with a twist, it's super helpful to call it something. You can call it something boring like I, something dramatic like zeta, whatever you want to do. Like we talked about on Thursday, I tend to use omega, capital omega. So this is representing this whole integral. So this whole integral is going to equal u times v, main diagonal, uv, so that's minus a third e to the negative 2x multiplied by cosine 3x. So there's uv minus the integral of v du. Is v du positive or is v du negative? So the bottom row is v du, and it is positive, right? Two negatives here. So it's positive. So that positive thing is going to go into this integral right there. So it doesn't affect that minus in front. It's still going to just stay minus. So that's going to be, let's get the constant here. That looks like a 2/3 to me. And then an e to the negative 2x times cosine 3x times dx. All right. And what you are going to notice, because both of these functions have this sort of cyclic property, is that that integral is about the same difficulty as the original. The only difference is there's a constant in front, which is not increasing the difficulty. All right, so that's where we're at. Now we're going to do it again. We're going to do integration by parts again. I am going to do this clever little trick where I make this a positive and I distribute that minus to the inside. Then I don't have to have the big brackets with the minus being distributed. So, second integration by parts. Super important that we use the same pattern or we will undo what we just did. So we're going to go trig function with the dv. And the constant could go wherever you want. I'll just stick it with the e. So we're going to have u is negative 2/3 e to the negative 2x. And then for dv, the trig function cos of 3x dx. Derivative over here, we've got to use the chain rule. Oops, that should become a 4. We're multiplying by the derivative of the exponent. Here we integrate. The integral of cosine is sine. Reverse chain rule. So we get that. Any questions on that setup there? The derivative. All right. So then we have this stuff out in front. Not the plus, but it's going to become a minus because we don't have to deal with any distribution, but this entire integral is going to become u dv minus integral of v du, and u times v is negative. All right, u times v is negative, so negative 2/9 multiplied by the exponential multiplied by the sine function. So there is uv. There is uv. Minus the integral of v du. v du is positive. That's cool. We don't have to deal with any sign change. Looks like the coefficient, looks like the constant is 4/9, and then an e to the negative 2x, and then a sine of 3x dx. Okay. Looking back at the original integral, we notice that they are the same, right? We have an e to the negative 2x sine of 3x. Don't we have a symbol that we're using to represent all of this stuff that I'm putting in yellow? Omega. That is omega, right? We said omega is going to be the integral of this stuff. Right now, we have, so I'm just going to use a little shorthand here. We're going to bring all that down. this is what we have, minus 4/9 times omega. This is just a linear equation now. And we're just going to twist those omegas from the right over to the left. On the left, how many omegas do we have? 1, which we could write as 9/9 if we want. So when we twist those ones over to the left, we end up with 13/9. Yeah? Is that a yes? So 13/9, everyone following that?
No.
So over here we have 4/9 omega, because the yellow here is omega and the constant factors to the front. So we have negative 4/9 omega. On the left side, we said the left side is just the original integral, which we're calling omega. And so we have 1 omega, which we could write as 9/9 omega, just so they have the same denominator. And then we add 4/9 to 9/9, getting 13/9. So now we have 13/9 omega. So this is the twisting part. And as soon as we do that, so we still have all this stuff out here in front. So we have all this. But as soon as I move that omega over, I'm going to put a constant of integration there. Omega is an indefinite integral. Its evaluation is a family of antiderivatives. There has to be an integration constant. That integration constant is kind of obscured inside the omega right here. As soon as we move it over to the left, though, we need to indicate that there is a constant of integration that's present. What do you think our last step is?
Divide 13.
Yeah, we can divide by 13/9, multiply by 9/13. Exactly. Our goal is we're back to algebra 1. We want to isolate omega. So we add the two like terms of omega together, we take the coefficient, divide it out, and we isolate omega. So this is back to regular algebra. So we're going to multiply both sides by 9/13. So 9/13. 9/13 is being multiplied across here. 9/13 being multiplied across. And this will be our final answer. So that is integration by parts with a twist.
Could you just leave the 9/13 undistributed, or would you have to distribute it?
Well, I want to say two things about that. So notice that I just wrote the C again. I didn't write 9/13C. When we're dealing with this type of thing, we can think of the C like a recycle bin, and if we multiply the constant by another constant, it's just going to stay a constant. So these two C's are different, but that's okay because this is sort of our final C. You could leave that 9/13 out, or 9/13. You could put it out in front and put all that in parentheses. You can do that, but that's best. We should distribute it just because there's simplification. But, yeah.
How do you get the 3/13 again?
So multiplying both sides by 9/13. So we're going to multiply this side by 9/13. If I can squeeze it in there. So 9/13 times 1/3. 3's cancel, giving us 3/13. 9/13 here. The 9's cancel, giving us 2/13.
Oh, right, because you're having omega by itself, so now when you're dividing it, switch it.
What you said. Okay. This one is for you to try. I took away all the extra coefficient garbage because you can just sort of feel the process without thinking about all the arithmetic. So you all start on this one. And let's see if you can add a twist to your integration by parts. I was just reading it.
Oh, okay.
Curiosity. Good. Yeah. What's the question? Oh. Oh, oh. Wait, say that again? Oh, it doesn't. Let's see, try to pull it up. Should. Oh. Do you have the app? Oh, really? Yeah, when you sign in, you'll need to sign in through school ID. That's the one. I guess there you're gonna just be signing in your Apple ID. But then once it's downloaded, then you'll wanna sign in with your school ID.
What's wrong with you? So it doesn't make sense.
Let's see.
And then I'll make it.
I like your symbol. It looks like there's a distribution that didn't happen properly. So I agree with that. So you, that, is that right? The derivative of cosine is.
Derivative, I didn't do that, okay.
There's where you lost your sign. Does anyone care where the cosine goes and where the e to the x goes? Anyone have a preference?
Cosine goes in dv.
Okay, you want to because that's a nice easy integral?
Yeah, because it's not negative.
Right. That's good logic. So if you put the cosine over here with u, you have to make sure when you differentiate you get negative sine of x. Yeah, if you want to avoid the negatives, then that's a good strategy. And then when we differentiate this exponential, it's just itself multiplied by dx. And then the integral of cosine is sine. So that looks good. And we're going to call this something. I saw different things. You can call it whatever you want. Saw a smiley face. That works fine. Whatever you want to call it. So I'll call it omega. It's going to equal uv. So that's e to the x sine of x minus the integral of v du, which is the bottom row. This is our moment of reckoning. Is this integral easier than the original? Nah, it's about the same, which is always going to be the case when we do the twist. When we do integration by parts with a twist. And then we're going to do integration by parts this second time. And we want to use the same pattern. If we let u be the exponential originally, stick with it. So we're going to let u be e to the x. We're going to let dv be sine of x dx. We will differentiate over here. Again, don't forget that dx. Oh, we have a minus sign. There it is. So let's see. So we have omega on the left is equal to e to the x sine of x. Oh, and I forgot to put the minus on the inside. So I just have to make sure I'm super careful. There's going to be a distribution. So uv is minus e to the x cosine x. uv minus the integral of v du. v du is negative. v du is negative, so that's going to make that a plus integral e to the x times cosine x. dx, close those big brackets. And what do we notice? Oh, this guy right here matches that guy, matches omega. Right, that is omega, or whatever symbol you use to represent. So this will end up looking like, once I distribute this minus sign, minus omega. So that is our simplified, once we evaluate all the integrals, replace the integral with omega. Now what do we do to both sides?
Add both sides by omega.
Add omega to both sides. How many omegas are on the left? 2 omega. And then on the right, we're going to have that same thing, and as soon as we add that omega, on the left we have an indefinite integral. And an indefinite integral is a family of antiderivatives, so there needs to be a plus c on the right. So I'm going to put that plus c as soon as I move the omega over. Last step,
Divide by 2.
divide by 2. Divide by 2, and we have found the family of antiderivatives that we have been looking for. And when you divide that constant by 2, we just rewrite it as just a general C. So if you're overambitious, you could take the derivative of that, and you get back to where we started, using the product rule twice. All right, any lingering questions? Yeah?
So this only works if you're going back to the same original function that you were working with.
Yeah, so integration by parts is when we end up getting back to an integral that matches the original. And it's only going to show up when we have an exponential with sine or an exponential with cosine. Those are when we're going to get the integration by parts with a twist. Typically. There is one example that's a little different that I'll show you. But for you guys, like on a test or anything in the homework, exponential and a sine, exponential and a cosine, where both functions have that cyclical nature when you're differentiating or integrating. Well, let's go to next chapter, next section. So integration by parts, that's another integration technique in our quiver. Our quiver is slowly expanding. Now we're going to look at something a little bit different. We are going to be integrating powers of trig functions. And we are going to primarily be looking at products with sines and cosines or products with secants and tangents. So here's our first rule of thumb. Integrating powers. If one of the powers is odd, so if we have sines and cosines and one of the powers is odd, split off a factor. So in this case, we have sine cubed. If we pull off one sine, we're going to put it over with the differential. We're going to group it with the dx. We're going to sort of think of the sine x dx as our differential. Then we're going to be left with an even number of sines, right? Sine squared. Or possibly if it was sine to the fifth, we pulled one off, we'd have sine to the fourth. And we can use the Pythagorean theorem to do what I'm saying right here. Convert the leftovers. So by leftovers, this is what I am referring to. So we have an odd power, so we're going to pull one off. So we pull one off, and it's going over to hang out with the differential. It's going to commingle with the differential. These are the ones that I'm referring to as leftovers. So the ones that are left behind after we pull one off. So pull off a sine, now we've got some leftovers, and we are going to convert the leftovers to the co-function. So sine squared, I want to convert them to the co-function, convert them to cosine. What does sine squared get replaced with if we convert to cosines?
1 minus cosine squared x.
1 minus cosine squared of x. All right, and I'm still sort of thinking of this together. Sine x dx. Now we can use u substitution. What u would we choose? So if we let u be cosine of x, What is the derivative of cosine?
Negative sin x.
Everyone agree? Negative sine x. And that's in the blue box over there on the right. So the whole idea of converting the leftovers is to convert into the function whose derivative is what we peeled off. So if we let u be cosine of x, then du will be minus sine of x dx. And the minus, you don't have to write this step if you don't want to, but the idea is that the sine x dx is going to be replaced with some constant multiple of du. So this will be the integral of 1 minus u squared du, and then a minus sign I can pull to the front. So sine x dx gets replaced with minus du. So we have minus, we integrate in here. And then we add a constant of integration. And the last step is to back substitute, get back to cosine, and I'm going to distribute this minus sign. So we're going to end up with minus cosine of x plus 1/3 cosine cubed of x plus c. So odd power with sines and cosines, pull one off, convert the leftovers. Converting the leftovers means using the Pythagorean theorem. Note down here, if both happen to have even powers, then you're going to do what we did in the last chapter and reduce the powers with the power reduction identities that we used in the last chapter. We're more interested right now in if one of the powers is odd. So right now, I'd look at that. Product of sines and cosines. Ooh, cosines to an odd power. So if cosines to an odd power, we're going to peel one off. So I'm going to leave a little gap here. I'm going to say, ooh, let's take one of those cosines, stick it over with the differential, put it in this little blue box. It's going to hang out there. What are we left with? If we pull one cosine off, we're left with
Cosine to the fourth.
cosine to the fourth. So notice that because cosine had an odd power, when we pull one off, we're always left with an even power on that cosine or sine or whatever. So that's easily converted. So these are the leftovers, right? We pulled off a cosine. These are leftover. They're hanging out. They're sad. They got left behind. Now we're going to convert them. We want to convert them to sines. So we have sine squared multiplied by, how do we convert cosine to the fourth?
One minus cosine squared squared.
1 minus,
Cosine squared squared. Or sorry, sine squared. I'm
yeah,
thinking-
1 minus sine squared squared. You got it, you got it. 1 minus sine squared squared. And we are going to let u equal Ethan? What are we going to let u equal? So if we put this cosine over here, we want to let u be the function whose derivative is what's in the blue box?
So it's for u equals the derivative of the u box.
So-
of the blue of cos x dx.
So what function has cosine as its derivative?
Sine.
Sine. So yeah, we want to let u be whatever the function is that's present over here. Like the whole point of pulling off a cosine is that if we let u be sine, its derivative is over there. If we pulled off a sine, then we're going to let u be cosine because its derivative would be over to the right in the blue box. So if we let u be sine, then du is cosine. And the nice thing about that is that, right, all this stuff just becomes u's. So the idea is whatever function we put over with the differential, the one we peel off, we want to let u be the other function. And then that's going to turn everything into polynomial land. All right, cool. So here we're going to have to do a little algebra. All right, we're going to have to FOIL this out before we can integrate it. So we'll FOIL that. And then we've got that. And then we integrate. Add a constant. We end up with that antiderivative. So it turns into just a pretty routine polynomial to integrate. And then we just have to back substitute. We had a sine, so we're going to put that back in for the u. How's that look? So odd power, pull one off, convert leftovers, and then once everything's converted, the function that you're converting into is what your u is always going to be. All right, anyone have a question on any one of the steps? So, with these powers of trig functions, the ones we focus on are going to be the sines and cosines. And part of the reason that sines and cosines work nicely together is that they essentially are each other's derivatives. And then we're going to look at tangents and secants, and for the same reason. The derivative of tangent is secant squared, right? And so those are connected in a similar way. It's a little more complicated, which we'll see, but that's essentially the idea. All right, let's talk about the rule for secants and tangents. So if the power on secant is even, we're going to split off a secant squared if the power is even. What function has secant squared as its derivative? Tangent. So the idea is that if we can pull off a secant squared and group it in that little blue box on the right with the differential, then we're going to let u equal tangent, so that its derivative is over on the right with the differential. So right here, I'm going to sort of nominally do this. So I'm pulling off the secant squared, and we got an even power, but there's nothing left. There are no leftovers. Right? There's no secants left behind that need to be converted. So I'm just sort of saying, okay, well, I'm going to think in my mind that I'm going to group secant squared with the dx, and we're ready to do substitution right now. What's u equal to? Tangent, right? We can do it right away. We didn't have any leftovers. We took all the secants that were present became part of the differential here. So we're going to end up with just u squared du. Right? Not too bad. So this will be 1/3 u cubed plus c. We do our back substitution. And we've got that. Okay, so if secant is to an even power, we split off a secant squared and convert any leftover secants. Okay. Next one. If tangent is to an odd power, we're going to split off a sectan. What function has sectan as its derivative?
Secant.
Secant. So if we pull off sectan, we want everything over here to be secant, so we can let u be secant, and then its derivative will be the sectan. So, if tangent is to an odd power, pull off a sectan. Is there a secant here to pull off a sectan? So tan is to an odd power. We're told if tan is to an odd power, we want to pull off a sectan. There is no secant, so what do? Magic bullet? Multiply by 1. And the form of 1 will be secant over secant. So the rule says if tangent is odd, pull off a sectan. If there is no secant present, we create one. We have magical abilities. Use them. Okay, so we're pulling off a sectan. If we pull off a sectan to put over here with the differential, this is going to be our blue box over here. Okay, so we're focusing on pulling off secant tangents. We know that the derivative of secant is sectan. So in this context, these guys are the leftovers. We want to turn all the tangents into secants so that if we let u be secant, its derivative is in that blue box right there. So, how do we turn tangents into secants?
Secant squared minus 1.
So we go back to that circle I showed you that is the best visual imaginable to remember this identity. So if we go to the unit circle and we extend beyond theta, we extend beyond the terminal ray there, if we look at this triangle, that is the best way to visualize and to remember this identity, unless you want to do algebra. So we talked about why that was last week. So we're converting a tan squared. We look up here, this side is tangent, so if we square that, it's going to be the hypotenuse squared minus 1. So secant squared minus 1. And then we're ready for our u substitution. So now we let u be the secant of x. du is going to be sectan. So we end up with that. What do you think we're going to do with that u squared minus 1 over u? Separate it. So we're going to distribute that u. So we get u minus 1 uth. So the integral of u is u squared over 2. What is the integral of 1 over u?
Natural log of absolute u.
Natural log of absolute u plus c. Final step, back substitute. We said we were going to let u be secant of x. So we'll have half secant squared minus natural log absolute secant. Plus c. That'll be our antiderivative. That'll be our final answer. All right, questions on products of powers? You didn't get to work one yet, but you'll get to work some tonight in your homework, and I'll let you work some more on Thursday. Sebastian?
Can I look at the rule again? For
Yeah. So the rule for secants and tangents, even secant, pull off a pair. Odd tangent, pull off a secant times tangent. And if neither of those are true, Then we'll look at this one next time, but then we'll do something else. The two primary things are if tangent has an odd power or secant has an even power. All right, we'll stop there. See you Thursday.
How'd you get the ln of it, or you?
Oh, say that again?
How'd you get the ln?
Integrating 1 over u.
Guess we separated.
Oh.
Do you see it? So yeah, we separate right here. So I'm distributing the u into the u squared and distributing it into the 1. So splitting the fraction.
Okay.
And then integral of u and the integral of 1 over u separately. Make sense? All right, see y'all Thursday. I'll be sticking around if you have any questions. As long as you want. Thanks for coming, Stephanie. Sure, yes.
It's kind of perfect time that it started. It was right at the end that I started getting confused. So it's like everything else was like, you know, it's like cut off at the perfect time.
Yeah, exactly. Don't get too confused. That's what's hard about 2 hour and 15-minute class.
Right, yeah.
You got
It's
it.
about a question. It's gonna.
Sure.
It's gonna sort of, but on the I said I got this one wrong, but just because it didn't have a parentheses around it.
Oh,
but
yeah, 'cause you have.
I usually,
yeah,
I
there's
don't know,
drawings,
it just,
right?
it was,
Yeah.
I usually.
So yeah,
that
so
over.
it's
But,
yeah. So the issue is
I
that
have an hour.
Yeah, the
to
only-
get ready for my chemistry.
have you already taken it twice, or did you just take it once?
No, it was the last,
Yeah.
the one from, like,
Yeah.
chapter 6.
Right. Did you do it twice, or
Yeah.
oh, because it's already passed.
Yeah.
Yeah, I would definitely give you. I'll give you the most credit on it.
Not that I.
I mean, the only issue is that that is different than this.
Yeah.
And you see that?
Yeah, I was looking at it, it's basically the same thing, because like sometimes it doesn't make you put parentheses, and sometimes it does, and I never know which to put.
So usually the rule of thumb is whether it's plus or minus, whether it's plus or multiplication. Like if we had something like 17 cosh, there we normally don't do it.
Okay.
If it's multiplication, that's considered one group. That would never be considered natural log of 17 times cosh. But with addition, you have to put it because it's ambiguous if you weren't going to put it. So yeah, send me an email so I'll go in and give you, like whatever.
Thank you.
Point 8 or something. Something a lot more than 0.
Yeah.
Something more than 0.
Thank you.
What happened to the Nuggets?
I don't know. I don't want to talk about it. I think we'll do okay this year.
Yeah. I was so disappointed last year.
I was too. I was like, dude, what is Murray doing?
I know,
was
it was
so
sad. It was all of a sudden.
He was so good, and then last season, I think he's getting it back though.
I hope so.
I think so.
I hope so.
I hope
Because
so.
that was so fun. So fun having a.
I thought, yeah, we lost to the Timberwolves, right?
Mm-hmm.
Yeah, we'll beat them this year, bro.
Yeah.
I think.
Sounds good.
I think we'll make it.
How's the math coming?
I feel good about this. I feel a lot better about this stuff than the last stuff.
Good.
The last units, I was on like 4 hours of sleep on the exam. I think that might be why I did so bad. But the this feels pretty good. I did
Good.
I'm trying to stay ahead of it.
Yeah,
I'm trying to like look at it before I come to class. I think it's making a big difference.
That makes a huge difference. Because there's so many things going on that if you can look at it ahead of time, it just orients you so that you're not like tossed into the rambling water.
Yeah, because last Thursday when we got an integration by parts, I was like, what is going on? And then
Yeah.
I like did a couple examples. I was like, okay, this is not hard at all.
Yeah.
I mean, it is, but
It is, but the nice thing about it is that it's sort of back to that algebra thing where here's a procedure.
yeah.
Whereas with a lot of the stuff in the first unit is like, okay, well, you have to visualize your cross sections and visualize, a lot of things that are, kind of abstract. This is a little bit more like, here's how you do it.
Yeah,
Follow this recipe.
I think I have to go back to the first bit a little bit.
Please.
Just, I mean, like I know, the
Well, I was
logic
helping you in the
gets
math
me.
center, and you were doing, you know.
I was getting it slowly.
You were super close. You were like, you know, like right there.
Yeah,
It was
it's like
just
that
a-
last part, and then the algebra. I mean, the whole arc length stuff and the surface area.
Yeah, that's.
That stuff's tough.
That
I
stuff's
kind of accepted my fate. I was like, "There's no way I'm gonna get this down
Yeah,
before
that's
the test."
That's the hardest stuff for sure in that
Because
first unit.
what do you have to do? The perfect square trinomial thingy? That's what I can't get.
Yeah,
And I
that-
remember on the test, I was like,
That's.
I felt good about the surface area, and I get to that, and I was like, okay, I know, like he has like the perfect square trinomial right
Yeah.
here, but I don't know how to get it.
Yeah. Yeah, look at that answer key, you know, before it gets too far back in your brain. And,
Yeah, I was gonna redo the ones, and then I know I screwed up on the Kosh ones too, which those are honestly I feel like I should have got because
You
it's
should've.
kind of similar to this.
It's very
like,
similar.
It's just like follow the steps.
Yeah.
You don't really have to think about it.
Yeah, as we start to get into this, hopefully U substitution is becoming a little more obvious.
Yeah.
And it's like the idea that the whatever you pick for U, its derivative has to be there somewhere. You know, so if we pick U to be tangent, we see its derivative up there.
Yeah,
So it's
I think I do prefer integration by parts. Like
it's fun, right?
for the ones that like where I do it and I'm like, okay, this is easier. Like I just feel better about
Yeah.
doing it instead of U sub because I still do screw up U substitution a little bit.
Yeah, U sub takes a little more ingenuity, a little bit more, you know, you have to be able to, it's a little more abstract.
Mm-hmm.
Integration by parts, like, okay, I'm gonna let U be this, I'm gonna let dv be that, and, you know, if it doesn't work, I'll just switch them.
I think the U sub gets me because sometimes it's like the dx, you have to make it a negative, or sometimes I divide it by 2, and sometimes it's like really not clear to me. So that's I don't know. I'm getting there.
Yeah, you just have
I'm definitely getting there.
A little bit more practice and you will get it.
All right. Well,
Yeah.
thank you.
Absolutely. I will see you Thursday.
Yeah. Have a good weekend or Wednesday.
Not yet.